Hello everyone, welcome to this first lecture of this subject CAD-CAM, and in this we will see this finite element method. Okay, so this is Mr. Suyog Patil, Assistant Professor in Department of Mechanical Engineering, Sharad Institute of Technology, College of Engineering, Yadrao, Italkanji. Okay, in this subject CAD-CAM, today we are going to see the introduction to the finite element method FEM. Okay, so what is mean by this FEM, finite element method? Okay, this finite element method is a method which is used for this numerical solution of this field problem. Okay, for example, this is a problem, and if we want to calculate this values, okay, then this can be solved by numerical method. Okay, and this finite element method use a method for this numerical solution. Okay, so this is the method which gives this numerical method, okay, for solving differential or integral equations. Okay, in this finite element method, this method gives the solution by solving this differential or integral equations. Also, this method has been applied, okay, to a number of physical problems. This finite element method can be applied for a number of physical problems where this governing differential equations are available. Okay, in these differential equations or integral equations are available. Okay, in that case, this finite element method can be used for any engineering system or any engineering problem. Then again, this finite element method or finite element analysis is a computational technique. This is a technique, okay, or numerical method which gives us approximate solutions to this complex engineering problem. Then first of all, this description of this finite element method, this FEM cuts a structure into several elements. Okay, so this is for example, suppose this is an example of this gear tooth. Okay, and this is divided into number of small pieces. Okay, now this engineering or this problem is divided into number of small elements. So these are the elements of this. Okay, this is divided, cut, the structure is cutted into several elements, pieces of the structure. Okay, then it reconnects. These elements are can be reconnected at these nodes. Okay, by using these pins or by using drop of the glue. Okay, in order to hold these elements together. Here, this glue or pins are used to reconnect these elements. Then this process results in a set of simultaneous algebraic equations. Okay, so therefore solving this problem by using this finite element method, so we will get different equations. Okay, simultaneous equation, one equation for this element, one equation for the second element, third element, fourth element, fifth element. Likewise, we will get number of equations for the number of elements. Okay, by solving these equations, algebraic equations, we will get this approximate solution to this problem. Okay, in this finite element method. This finite element method essentially consists of assuming the piecewise continuous function. Okay, here this piecewise or number of elements, and this gives this for this solution, and this method obtains the parameters of the functions, which reduces the error in the solution. Okay, so therefore after solving this problem, this method can reduce this error in the analysis or solution. So by solving this number of elements or number of simultaneous equations. Then application. Okay, so there are some of the common applications of this finite element method. So this can be used in the equilibrium or steady state or time dependent problems. Also, this finite element method can be used in eigenvalue problems and in propagation or transient problems as well as. Okay, so this equilibrium or steady state problem means here we need to find out the steady state displacement, okay, or stress distribution. Okay, in case of this solid mechanics problem, when we are going to solve this any structural problem or solid mechanics problem by using this finite element method. Okay, so in that case we have to find this steady state values of this displacement or stress distribution. So therefore in such application this finite element method can be used. Then in order to get this temperature value or heat flux distribution value in this heat transfer problem, or we can say pressure distribution in case of the fluid problem. Okay, so in such applications, this time dependent applications or problems, this finite element method can be used. Then in case of this eigenvalue problems, some critical values of the certain parameters. Okay. Along with these steady state parameters, if we want to calculate some critical values of the certain parameters, okay, in addition to this corresponding steady state configuration, this FEM can be used. And in these problems, we need to find the natural frequencies or buckling loads and mode shapes in the solid mechanics problems. Okay, that means here we are going to calculate the displacement or stress distribution. Along with this, if we want to calculate the natural frequencies, buckling loads, or the mode shapes, so this eigenvalue problems, in such a problems, this finite element method can be used. Okay, in this propagation or natural transient problems, these are the time dependent problems. Okay, these are the time dependent problem where this is used where when we are interested in finding the response of a body under time varying force. Okay, when if we are interested to calculate the time response problem, so in such problems again we can use this FEM, or we can say the sudden heating or say heating or cooling. That means this heating and cooling is depends on this time variation. Okay, time dependent problem. So in such a fields, this finite element method can be used. Okay, these are the few common applications of this finite element method. Then features of this FEM. The piecewise approximation of the physical fields on finite element provides good precision results. So that means here in this finite element method, we are going to calculate this piecewise approximation solution to the any engineering complex physical problem. So in this method, we will get a good precision results. Okay, even with simple approximating functions. So again we can say the increasing the number of elements we can achieve any precision. Okay, so that means this piecewise approximation or piecewise dividation, discretization, by increasing this number of elements we can achieve the required precision, or we can achieve the required accuracy of the results. Then locality of approximation leads to a sparse equation system. Okay, for this discretizer problem, and this helps to solve problems with very large number of nodal unknowns. Okay, this finite element method also gives this helps to solve these problems with large number of unknowns. These are some features of this finite element method. Then finite element method, how this FEM can be worked. Okay, so these are the main steps here, finite element problem solution procedure. Okay, so first one, it is discretize the continuum. So first step here is the discretization of the continuum, means it is the dividation of the solution region, okay, into a finite elements. Okay, so the problem that we are going to solve, that we have to divide into number of small elements. Okay, so this is the first stage. Then finite element mesh is typically generated by a preprocessor program. Again, in this finite element method or finite element analysis, so there are three main phases. One it is called as preprocessor, second one it is called as solution, and third one it is called as post processor. Okay, this first step, discretization of the problem, comes under this first phase, that is preprocessor program. The description of this mesh consists of several arrays, okay, and which are nodal coordinates and elements connectivities. Okay, this description of this problem gives this, the discretization gives this several arrays and coordinates, nodal coordinates and element connectivities. Okay, then second step here is select interpolation functions. Okay, so therefore these interpolation functions are used to interpolate the field variables. Okay, so in order to interpolate the field variables, these interpolation functions are used here. Then polynomials are selected as interpolation functions. Polynomial functions are used or selected for this interpolation functions in this finite element method. The degree of polynomial depends upon the number of nodal values assigned to this element. Okay, so that means here the degree of polynomial equation depends on the number of nodes assigned to this element. This is the interpolation, selection of the interpolation of the functions is the second step in the finite element method. After this interpolation, selection of this interpolation functions, third step is find the element properties. Okay, after selecting these interpolation functions, we have to find the element properties. So the matrix equation for all these finite elements should be established, okay, and which relates the nodal values of this unknown function. So that means here these element properties, unknown values of this element properties can be solved by this matrix equation. Then again, for this task different approaches can be used, okay, and the Galerkin method or variational approach are some of the convenient methods for this calculating these element properties. After this third step, the fourth step, it is assemble the element equations. Okay, that means here we have to form the element equations or system or assembly of the systems, or we can say the global matrix equation. To find out the global equation system for this whole solution region, we must assemble all the elemental equations. Okay, here we have prepared this elemental equation. So in order to get this final solution to this global system or this global problem, okay, we have to assemble all these equations into a global equation system. Okay, and in other words, we must combine these local elements or local elemental equations for this complete problem. We must combine all the elemental equations into a global equation system. Okay, this is the fourth step of this FEM, that is assemble the elemental equations. Then next to that is solve these global equation systems. Okay. The finite element global equation system is typically sparse. Then again we can say the symmetric and positive definite system. Okay, so this in this step, in this global equation system, while solving this global equation system, we can directly solve these global equations, or we can use iterative methods. Okay, and iterative methods can also used to solve these equations and in order to get this solution to the problem. Okay, after solving these equations, assembly equations, we can calculate the additional results. Okay, compute additional results is the next step in this FEM method. And in this step, and in many of the cases, we need to calculate additional parameters. Okay, along with this some parameters, additional, we have to calculate additional parameters in many of the cases. For example, in mechanical problems, strain and stresses are the basic things that we need to calculate. Along with this, in additional to that, the displacement and buckling can be calculated in this solid mechanics or mechanical problems, and which are the obtained after solution. So in this additional results we can calculate in the step number 6. Okay, so these are the steps in this finite element method, and this FEM works in this few steps. Okay, brief history of this FEM, finite element method. Okay, the term finite element was first coined by the Clock. Okay, in 1960. In 1960, this Clock first introduced this finite elemental. Okay, and in the engineers used this method for approximate solutions of the problems. Okay, in such areas, that is stress analysis problems or fluid flow problems, heat transfer problem, and in some other areas also this finite element or this approximate solutions method can be used in 1960s. Then the first book published in 1967. Okay, the finite element method, the first book on the finite element method by this Zenkiewicz and Chung was published in 1967. And in early in the 1970s, this finite element method was applied to a wide variety of the engineering problems. Okay, in 1970s, this method was used for this variety of the engineering problems, and in most commercial software packages organized in 1970s. For example, Abacus, Adina, and Sys are some of the software packages available nowadays, and these are the used for this analysis of this finite element analysis methods. This is all about the journey of this finite element method. Now advantages. So there are few advantages of this use of this finite element method. This finite element method can be readily handle very complex geometry. Okay, this complex geometry can be handled or can be solved with the help of this finite element method very easily. So also this can handle a wide variety of the engineering problems, for example solid mechanics problems, then dynamic problems, heat transfer problems, fluid flow problems, then electrostatic problems. So wide variety of the problems can be handled by this finite element method FEM. Okay. Also this can handle a complex restraints as well as, that means the intermediate structures can be solved here by using this method. Okay, intermediate additional problem structures can be solved. Then also this can handle a complex loading, for example a point load, or we can say the nodal load. Okay, nodal load on this element, then elemental load, for example pressure, thermal, inertial forces acting on the elements. Okay, so that means this type of this elemental load can handle. Then time or frequency dependent loading can also be handled in this finite element method. So these are the few advantages of this FEM finite element method. Similarly, few disadvantages are also there. Okay, it is a general closed loop form solution. Okay, which would permit one to examine system response to changes the various parameters. It is not produced. Okay, so variation in the parameters is not allowable in this finite element method. This is one of the disadvantage. Then again, FEM obtains approximate solution. Okay, this method gives the approximate solution to the problems. This is also drawback. Then this FEM has inherent errors because of these approximate solutions, or as well as discretization, or by using this number of elements it has some inherent errors as well as. Then mistakes by users can be fatal. Okay, this is very dangerous. So these are the few disadvantages. And the important thing in this finite element method is the discretization. This is the important step in this finite element analysis. The discretization is a process, okay, by means of dividing a given problem into a smaller regions which are called as elements. Okay, for example this is an problem, or this is a system, okay, that we want to analyze. Okay, so here we have to divide this whole system into small number of pieces or small number of elements. Okay, so these pieces are small pieces are called as elements. Okay, then again this the consideration to be taken in the discretization process are shown below. Okay, so or we can say we can divide this whole system or whole complete component into number of elements. Okay, so that means again we can here by using the one dimensional element, two dimensional elements, as well as three dimensional elements, we can divide this whole system. Okay, so by using this here we can say, see, by using this 1D bar element, okay, we can consider only one bar element here, and we can analyze this complete system by using this 1D element, or we can analyze this system by using 2D elements. Okay, 2D plane elements are here used to analyze this, or used to divide this whole system into number of elements. Or again here we can say 3D elements, okay, beam elements. So small number of pieces are considered here. Okay, 3D pieces. So by using these 3D elements also, this we can analyze, and this division of this whole system into small number of pieces is, this process is called as discretization. The process of modeling a body by dividing into an equivalent system of the many smaller bodies or units, and these are called as finite elements. Small elements, smaller parts are called as finite elements, and these interconnected at points common to two or more elements. Okay, these are called as nodes or nodal points. Okay, and the boundary lines surfaces is called as discretization. Okay, so we can see here, so this is the exact temperature distribution graph. Okay, this is the solution. We can divide this into number of small pieces. Okay, it is shown here, it is divided into 4 pieces, or linear interpolation model is used to divide this exact solution. Okay, and we got final solution here. Okay, similarly we can use quadratic interpolation model as well. As here in quadratic interpolation model, curved shape graph is there. Okay, Okay, so here we will get a better results compared to this interpolation approximation. Okay, so this method is called as discretization. Then field variable. Okay, field variable in the API. The field is the domain of interest and most often represents a physical structure. Okay, physical structure, or here we can see, so this is the physical structure or physical component. Okay, it is called as the field. Okay, this domain of the physical structure is called as field. The field variables are the dependent variables of interest governed by the differential equations. Okay, the field variables are the dependent variables of this domain. Okay, or differential equation, variables of the differential equations governed to this domain. And in the finite element approach, the nodal values of the field variables are treated as unknown constraints. Okay, that are to be determined. These field variables are treated as unknown constants to be determined in this finite element method. The interpolation functions are most often polynomial forms of this independent variables derived to satisfy certain required conditions at the nodes. Okay, so these are the field variables used in this finite element. Degrees of freedom. Okay, the degrees of freedom means the number of independent coordinates a structure can move. Okay, so for example, suppose this is a aeroplane. Okay, this is a structure which moves along this x-axis, positive x, negative x, which can move along this y-axis as well as positive y, negative y. Also, this can move along this z-axis as well as plus the z and minus z axis as well as. Okay, so therefore, this degrees of freedom means the number of independent coordinates along which this structure can move. Okay, so these are the three axes or three coordinates along with this structure can move. Okay, similarly, this structure can rotate along this x-axis, this can rotate along the y-axis, that means it may rotate along this y-axis, as well as this can rotate along the z-axis as well as here. Okay, so therefore this structure has 6 degrees of freedom along x-axis, along y-axis, along z-axis, and rotation about x, y and z-axis are the 6 different degrees of freedom. Okay, or generally we can say there are 6 degrees of freedom possible for any structure. Okay, for any structure 6 degrees of freedom are, and these 6 degrees of freedom are the movement on x, y, z axis and rotation about these x, y, z axis. Okay, these are the 6 different degrees of freedom for any structure or any problem, complex engineering problem. Friends, thanks for watching this video. If you like this video, please share, comment and like this video. Then subscribe to my YouTube channel and click on the bell icon to get notified for more videos on this CAD/CAM subject. And thanks for watching. Thank you so much.